So with that kind of background in mind, let's start to unpick what is happening in terms of oxygen uptake at the onset of exercise. Well, what we're dealing with is exercise pulmonary VO2. And so imagine now we're going to have somebody exercising. And so it begins to increase within the first breath. So as soon as the workload is applied, we'll actually see a very small increase in pulmonary VO2 within the first breath. And this is what we refer to as phase 1 or the cardiodynamic component. Now, what then happens, which is quite interesting, is there is kind of a brief cessation or brief kind of pause. It doesn't dramatically increase prior to the appearance of what we call the exponential increase of VO2. And it's around about 15 to 20 seconds later when phase 2 occurs. And that's what we call the fundamental or primary component. The end of phase 2 is where we get to phase 3, which is steady state. So there are the 3 phases in that curve. So although that curve looked pretty uniform that we've seen in previous diagrams, both from Jones and Paul and also from Astrand and Rodell, it's actually made up of 3 different responses. And these 3 different responses have 3 physiological foundations to them. Phase 1 starts as soon as load is applied. And it's got this around about 15 to 20 second window. So how do we move from phase 1 to phase 2? Well, phase 2 starts when you get the first, what we would describe as effluent from the exercising muscle. That is the first delivery from the exercising muscle to the lung of carbon dioxide. So the net result is that you suddenly get an increase in minute ventilation because of the CO2 coming to the lung. That drives up, and remember that's coming from the response of what's already going on at the tissue. That stimulates, and remember it's CO2 that drives respiration. It drives a respiratory response which triggers the increase in ventilation, which allows you to now pull in more oxygen. So the first arrival of this venous effluent at the lung triggers the onset of phase 2, and it's a very different response to what you're seeing in phase 1. And it's kind of mono-exponential in terms of what happens before we reach this steady state condition. And so don't worry necessarily about all the mathematics that are going on here and so on, but you can see this is breath by breath data here. And then this is that data which is fundamentally being smoothed. So here's the phase 1. So this is about a 15 to 20 second period. And it's what's called the cardiodynamic phase. You suddenly get this change in the response in phase 2. So this is where that first draft of effluent, that is the release of CO2 and other kind of byproducts, but mostly CO2 from metabolism, hits the lung. That then triggers respiration. Now you get this very sudden increase in the VO2 response, but notice that it slowly starts to level out. In other words, the gradient of response starts to reduce until you eventually reach phase 3 and steady state. So we have 1, 2, 3 different responses to the VO2 response to exercise. Now, all this is referring to in here, just to kind of clarify, is the mathematical ways in which we analyze this. So this formula here is the formula that describes this response that you see here. We use it to model the curve. All that we've got here is we've got data which allows us to calculate what is happening at any given moment in time. So I'm going to be interested in, well, how much does the VO2 rise by in any given phase, the amplitude. So how much does it go up in phase 1? What's the amplitude in phase 2? What's the amplitude in phase 3? I'm then interested in the time delay. How long does it take to leave phase 2 and move into phase 3? But we also use what is called the tau function. In other words, we use a fixed period in time. So we look for something which relates to 63% of that change, which gives us a fixed parameter to compare to. But you don't need to worry about that for the purpose of this session, but I thought it'd be useful just to explain what these points and these kind of numbers and letters mean on the image you see here. So again, this is from Jones and Paul. Here we've got this is breath by breath data. here we've got the steady states. This is baseline, it's about 25 seconds at baseline. You have an instantaneous increase in the external load. So we've already learnt now the ATP turnover rate and demand increases instantaneously. This is phase 1 here. So we move into phase 2 when the venous returns from the tissue into the lung, drives up respiration, drives up VO2 to meet that increase in ATP demand. And slowly, over time, that VO2 does start to match the demand until we reach phase 3 and we reach steady state. Now, this is data from our laboratory here in Cambridge. And what we've done is we've got this with breath-by-breath data. And I've used the colours here just to kind of separate things out. So this is somebody at rest sitting on the cycloergometer. And you can see that it's pretty stable. There's a little bit of fluctuation as one would anticipate, but that's fine. And this is what we use as called unloaded cycling. We've then got this very small block here, and this represents our phase 1. I couldn't label it, it's too small, so this is the phase 1 response. Then we go into this primary component here. Can you see the way that the VO2 rises very, very rapidly? And this is our fundamental O2 deficit. So if you imagine, I just want to follow this line, this is where exercise started at the 4-minute point. So the ATP demand when turnover rate goes up instantaneously, and it would level out at whatever this value is here. I mean, we haven't got an ATP value, and we know that because this is where steady state occurs here. So this becomes the phase 3 response or the steady state response. And you can see just by looking at the curve, there are 2, less so 3 because it's less clear, but there are certainly 2 distinct responses. The response in phase 2 is very different to phase 3. And as we've already started to learn, the response in phase 1 is different to those 2 as well. So very, very different physiological conditions. So let's see if we can unpick particularly the phase 2 response. What does it actually reflect? We've understood what triggers it, but we haven't actually understood what it is, how it manifests. Well, the magnitude of that deficit, and remember that we said that the magnitude of the deficit is a function of the exercise intensity. And it's a function then of the amplitude of the VO2 response. So the greater the exercise intensity, the greater the VO2 response has to be, because you need more oxygen to meet the ATP demand in the tissue. So, and it's a function of the amplitude of the VO2 response at steady state, so phase 3, minus the VO2 just before the start of exercise. So in other words, the magnitude in this phase here is the VO2 in phase 3 minus the unloaded VO2 here. That gives us the magnitude or the amplitude, one might describe it, for the phase 2 response.